Okay, I guess 8 o'clock is always a challenge. Good morning and good evening to you guys. There are only 2 there. There are only 5 here. Maybe others will trickle in. We will see. Maybe after the first assignment, things are getting tough. How are you guys doing on the assignment at the PI? I've had a few requests for extension. And I just want to get an idea of how many of you would benefit if I extend it after the Mardi Gras holiday here. That's Wednesday is half a day, is it? When does the school start? Wednesday afternoon?
They're supposed to return.
Does anybody know?
I think it's usually Wednesday at noon.
Wednesday at noon.
That was last year. I'm not sure about this year.
So I will update the revised due date on Moodle, and so we will extend it for the benefit of those who are doing struggling with MATLAB still. Okay. So are there any questions for me from the students at the PI? No? Are you able to see the screen? You are not able to see the screen? Oh, share my screen. Thank you. How about now? Are you able to see the screen now? Okay, thank you. We're all there. Okay. Okay, all right. So if you are having difficulty or need help with the assignment 1, email me, and we will set up a Google Hangout or something where I can take you through MATLAB session. And we will extend the due date to next week after the Mardi Gras holidays here. That will be after next Wednesday. Okay. So let's start with the. Are there any questions here? I don't want to be biased to paying attention to them. Any concerns, any questions?
When you say comment on something, do you want to just put like a comment symbol in MATLAB, and is that good, or do you want a separate page?
Yeah, the question is when I ask for comment on some observation, is it okay if you put %sign in the MATLAB script and comment on that? That's perfectly fine. If you choose to write it or put it in Word document, that's fine too. But if you're doing it as a report generator, it's probably convenient to put it in a comment, and that's perfectly acceptable. Yeah. Any other questions? Yeah.
How do you code vectors which start like a number and then have a bunch of zeros and have an end number, so you can't use a 1's command or 0's command?
Right. How do you code a vector which has one number followed by lots of zeros, followed by
the B vector?
The B vector, right. So I'm going to go into MATLAB a little after I cover the inverse iteration, and then I will show you in MATLAB how to exactly do that. Okay, it's not very difficult. You just need to know.
Yeah, I just know the code.
Right. I will show you. Have you used MATLAB before, or not before this class? Okay. So that is my concern. There are a number of students who have not used MATLAB before this class. And I don't want to kind of leave them out, and to keep pace with it. If you have questions like that, feel free to come and reach me out. And here you can drop by my office, but at the PI, you can always email me and ask me specific questions. And we will set up a special online session if you want to answer those questions. Okay, but remind me when I go into MATLAB. Remind me if I forget. Okay. Any other questions or comments? Okay. So in the last class, we looked at, I guess, the iterative refinement of the Gaussian elimination. So we introduced the idea of how direct method gives you solution in a finite number of times, but introduces errors that cannot be gotten rid of because of the direct nature of the calculations. Whereas an iterative method by design is designed to get rid of errors. You introduce a very large error as an initial guess and it successfully gets rid of them. So by combining these two, we can get the advantage of both the direct method and the iterative method. And we looked at the concept of a linear independence, and we also developed the Gram-Schmidt procedure. So we're going to use that a little bit today. The basic idea is if you're given a linearly independent set of vectors, you can represent any arbitrary vector as a linear combination of them. But you can also orthogonalize them, make them perpendicular and orthonormal. In fact, you can normalize that. And we saw an algorithm for doing that, and I gave you a piece of MATLAB code to do that. And then we introduced the power iteration for finding the largest eigenvalue of a matrix. Often, we don't need all the eigenvalues, particularly of a very large matrix, but we need the largest or the smallest or some eigenvalues in a certain region when we look at stability, and we will see later on. We already saw one situation where we need the eigenvalue, the largest eigenvalue, that's a spectral radius of an iterative scheme. Okay? So the stability of numerical schemes as well as the physical stability of a dynamical system are essentially determined by very similar ideas. Okay? So this goes by various names: normal mode analysis, spectral analysis, etc. They are essentially the same ideas that we are introducing so far. So power iteration, we saw, gives you the largest eigenvalue, and we saw why it does that by doing the spectral representation of an arbitrary vector. Okay. So if I want to find the smallest eigenvalue, what can I do? And the answer is the so-called inverse iteration scheme. Okay. So the eigenvalue problem is Ax equals lambda xi. If A is an n by n matrix, you have n eigenvectors and n eigenvalues. Okay. So if I pre-multiply this by A inverse, then I will have A inverse A, which will give me the identity matrix, and on the right hand side I will have A inverse xi. Okay. And I can rearrange that in the following form. That is, take the lambda I to the left side. Okay. So 1 over lambda I times xi equals A inverse xi. So if I look at this, that also looks like an eigenvalue problem. Basically, I have a new matrix A inverse. I multiply it by a vector xi. It gives you a new eigenvalue multiplied by the same vector. Okay. But the matrix now is A inverse. So if I know A, I can find its inverse. And the idea is, if I apply this power iteration scheme, okay, that is, make an arbitrary guess for a vector and multiply that by A inverse, not A, by A inverse. Keep doing that. And what you will find is that it will converge to the largest, of course, power iteration always converges to the largest eigenvalue in the eigenvector. Okay, so it will converge to the largest eigenvalue of A inverse, but that is the 1 over lambda I, right? So if you call that as mu I, the largest value of mu I will correspond to the smallest value of the original matrix lambda I. Okay, so that's why it's called the inverse iteration, and it gives rise to the smallest eigenvalue. I learned to use the pen. Ratnesh actually helped me figure this out this morning. So apparently, if I touch with two touch, it always gives me this. And I was doing with one finger, but my next finger, without my knowledge, was going near it. So it always puts up this. And Ratnesh was the one who kind of helped me figure this out. And if I use the pen, I avoid the problem because I keep the distance from there. This is a comment for guys here. You cannot follow what I'm saying at the PI. But hopefully it should go smoothly from now on. Okay. So that's the basic idea, that you can get still the largest eigenvalue of the inverse matrix, which will give you the smallest eigenvalue of the original matrix. Now, what does this entail from an implementation point of view? If you give me A, I need to find the inverse, okay? And then I multiply this by, I guess, maybe a nuisance. Let me just close my, so that it doesn't occur again, okay? So I start off with an arbitrary matrix that I assume, and then apply the matrix product, but I can find the inverse once, and then it's just a matrix multiplication. But inverse is still a very time-consuming task to find. So the question is, can you construct a more effective way that we have seen, based on what we have seen? Okay, so that would bring us the idea of an LU decomposition. Okay, so I can write this as A times yp plus 1 equals zp. Okay, so I'm not really inverting it in this. This is the kind of techniques that you should feel comfortable in developing to introduce efficiency in your calculations. Okay, instead of inverting it, I'm just taking it this way. But the problem that I have now is, I know what zp is. This is the guess I'm making. Okay, so that is the guess vector. Okay, so I know that, and I know A, and I don't want to take its inverse, okay, and store the inverse, because it's a fairly, particularly for large matrices, it's a fairly tedious task. But I need to find out what yp plus 1 is. Okay, now this is of the type Ax equal to B, where I know the B vector on the right hand side, I know A, I need to solve for this. Okay, so here you can do an LU decomposition. Yp plus 1 equals ZP. Okay, so I need to do the LU factor only once and store it, and I will have different right hand sides. These are the successively improved guesses, and I can find out the new vector yp plus 1 and scale it and implement a very efficient scheme using the LU decomposition. Any questions on that? Any questions? No? How about the guys at PI? Any questions? Are you guys hearing me all right? Just to see whether you're paying attention to me from time to time. All right, okay, good. So this allows us to get the largest or the smallest eigenvalue of a given matrix. Okay. The next idea is, if I have to find the eigenvalue in certain region of the entire spectrum of eigenvalues, you can always look at these eigenvalues as being plotted on the real part of lambda I and the imaginary part of lambda I. So if I have, for example, a 100 by 100 matrix, I'm going to have 100 eigenvalues. They can all be complex. They can be real, but they can be complex as well. Okay, so I can plot all of them at different locations as just points. So I will have 100 points, and I'm putting them deliberately on the left-hand side because the system is stable. You must have the real part of the eigenvalue as negative. So if all the eigenvalues are on the left-hand side, it indicates that we have a real system. Okay, so this is where we will need to calculate an eigenvalue that just crosses the imaginary axis. If some eigenvalue crosses the imaginary axis, it can cross in many ways. It can cross like this, simple real negative value to positive value. It can cross like that. It can cross like that. Okay, so we need to be able to make the distinction between each one of these. Each one of these will give rise to different types of dynamical behavior that we will see later on. So at this point, all we need is to develop a more general tool that will allow us to calculate the eigenvalues in certain neighborhood. Okay, so if I give a particular selected eigenvalue sigma. Sigma can be complex. Okay, so I say that I want to find the eigenvalue in this neighborhood, for example. Okay, the eigenvalues that are closest to that particular point sigma I. So sigma I is a known quantity. This is known, and A, of course, is known. Okay, so how do I set up an iterative scheme that will converge to eigenvalues in that neighborhood? Of course, remember, power iteration always converges to the largest eigenvalue. So we need to trick the system in such a way that eigenvalues in that region appear to be the largest eigenvalue to some modified matrix. Okay, the original matrix will have the largest eigenvalue. Power iteration will always go there. Okay. So if I take this problem, A minus sigma I inverse xi equals mu xi. Okay. So I can once again do the same manipulation, that is take mu I to the left hand side and A minus sigma to the right hand side, and then expand it as AXI minus sigma IXI. Okay, this is simply an expansion. And AXI is the same as lambda xi. Okay, so this term is the same as lambda times xi. I replace that, and of course I have sigma xi once again. So I can factor this out, lambda I minus sigma xi. Okay, so so the eigenvalues of this matrix A minus sigma I. So this is the power iteration. I'm going to set up the power iteration on this scheme. Okay, so you give me a sigma, I formulate a new matrix, and which is A minus sigma I take its inverse, and then I apply the power iteration on that. Okay, but that is equivalent to, from this one, we can see that relationship between 1 minus mu I times xi equals lambda I minus sigma xi. So xi is the same vector on both sides. So I must have lambda 1 minus mu I from here, 1 over mu I is equal to lambda I minus sigma. Still the resolution of the pixels is not very good in this pen. Okay, so I can write lambda I is 1 over mu I sigma. Okay, so I can find the eigenvalues of the new matrix mu I by applying the power iteration on this. Okay, and if I know that, and if you give me what sigma is, I can find the lambda I of the original matrix A in that neighborhood of sigma I. Okay, so I recover my eigenvalues near sigma I from this equation. But the power iteration that I need to apply is this one. Okay, so the original matrix minus sigma times I. Sigma is a known number, the neighborhood of which I'm interested in searching for the eigenvalues. Take its inverse, and this is your guess. Start with an initial guess, and then apply the power iteration, the standard power iteration algorithm on that. Okay, so if you write one power iteration scheme, then by passing the correct matrix to that, you'll be able to solve all these kinds of problems. Okay. And once again, you have to find the inverse, but the most effective way of handling that is through LU decomposition. So you take this to the other side, and you have A minus sigma I times yp plus 1 equals zp. But here zp is the guess vector that you know. This is a number that is given to you. A is a matrix that is given to you. So you need to find out yp plus 1 using LU factorization. Okay, so by using new right hand side every time, you do the LU factorization once, and that's a better way of implementing it for large scale problems. But in an assignment, if you write one power iteration scheme for small matrices by 5 by 5, you can simply pass this matrix to it and use the original power iteration scheme, and that will work for 10 by 10, even 100 by 100 matrix. It will work in reasonable amount of time. I'm talking about reasonable meaning within a few seconds. But for 100,000 matrix by 100,000 matrix, you wouldn't want to do this implementation, but you would want to go for the LU factorization scheme. Okay, any questions? Okay, I have a piece of MATLAB code illustrating all these, and I was actually going to go into MATLAB and do that part. Okay, so create a tridiagonal matrix which is non-symmetric. Okay, now symmetric matrices are always nicer to handle because they will always give you a positive definite matrix, and you know something about the properties of the eigenvalues. Okay, they'll all be real. If it is complex, it will always occur in conjugate pairs, etc. Okay, so I'll just go through it quickly, and then we will apply the power iteration on some of these matrices and see how it works. Okay, so I just create in this case, a 4x4 matrix, and I have a function called TRID, and I guess I will put these functions. Well, they are listed, I think, here. If not, I will make sure that I upload them to Moodle. So I wrote a power iteration scheme, okay, and I will show you the code also. And it just takes that matrix T and then returns the eigenvalue and the corresponding eigenvectors, okay. And you can check that against built-in eigenvalue routine in MATLAB by passing the same matrix to TIG and picking the maximum value of that, okay. So this gives you all the eigenvalues. So it will give you a vector of eigenvalues. In this case, 4x4, so it will give you 4 eigenvalues, and you can pick the maximum from that. And here we have from the power iteration. Okay, and you see that it is the same value. Okay, and when you do the smallest one, all I did was the same algorithm, but I passed directly the inverse. So this is not the efficient implementation. Efficient implementation will require you to do LU factorization. Okay, but here I'm just inverting the matrix and passing to the same power iteration, and what it returns, I call it as mu, and so 1 over mu is my lambda. Okay, so mu is the largest eigenvalue of the inverse of that matrix, which should turn out to be the smallest eigenvalue in magnitude. Okay, and same, I'm checking that against what MATLAB will return by using EIG function, but passing it to the MIN function, which gives you the minimum of a vector. Okay, and there is probably one for the shift. Oh, that is the same. I don't know why I repeated it twice, but here is the shift one. Okay, find the eigenvalue closest to 2.5. So I set sigma equals 2.5, and I formulate this matrix T minus sigma identity. EYE is a matrix function that creates an identity matrix of the prescribed size. So T is 4x4. So I form that matrix and I invert that and I pass it to the power iteration. Okay, and it gives me a value mu, which is the largest eigenvalue for this matrix. Okay, mu is the largest eigenvalue of that matrix, but I know that it is related to 1 over mu plus sigma. So lambda, that is the eigenvalue closest to 2.5. Okay, I wanted to find the eigenvalue that is closest to 2.5. So they are related by this. So lambda is sigma, which is 2.5 plus 1 over mu. Okay, so the closest eigenvalue turns out to be 2.87. Okay, and here you see that. These are the 4 eigenvalues, but the one that is closest to 2.5 is that. Okay, so it really works well, a very efficient method in terms of computational load. And the generalization of this, there is a whole lot of theory, and the book by Saad and by Wilkinson on algebraic eigenvalue problems will take you through all the variations on this. What happens when you have the largest eigenvalue occurring with the multiplicity of 2 and 3 in degenerate cases like that. Okay, but for our purposes, there is one thing that I found extremely useful as a studying engineering problem is a method called Arnoldi method, and I will mention that. It is available in MATLAB now. 10 years ago it was not available, so we developed our own code to implement that in Fortran, but now I think it is available in MATLAB. What it does is, power iteration gives you only the largest eigenvalue, but if you are interested in a cluster of eigenvalues, 10 largest eigenvalues, or 10 smallest eigenvalues, or 10 eigenvalues nearing a neighborhood. Okay, this method will allow you to construct that. And the way it does that is, whenever you do a power iteration, you make a vector, multiply it by the matrix, you get a new vector, right? So it keeps track of 50 such iterates, 50 such vectors that forms a subspace, and then it builds an iterative scheme in such a subspace. This is why it is important to understand this idea of orthonormalization, Gram-Schmidt procedure. These are the ideas that are very simple but used repeatedly to build more sophisticated algorithms. Today, in fact, I'm going to do a conjugate gradient method. Okay, that also uses a Gram-Schmidt orthonormalization procedure. And it's a very simple iterative method, and it's very popular in COMSOL and other places, in Fluent also. For large linear systems, that's a very successful iterative method for solving linear systems, and this is a successful method for solving eigenvalue problems. Not all the eigenvalues, but a cluster of eigenvalues that you are interested in some region. Okay, maybe at this stage I'll go into MATLAB and show you and answer that particular question, and then we'll come back and look at spectral representation of solutions. That will set the stage for us to develop the conjugate gradient method. So, that is a one-line program that constructs the tridiagonal matrix, given the lower triangular, the lower diagonal, the diagonal, and the upper diagonal elements, and the size of the matrix. Okay, so it's a very compact way of doing it, using built-in functions. Where did it go? See, I didn't even touch it. I have to stay away from this screen. It's too small, I think. Okay. So it uses a function called once, and that is the key to your question too. There is a built-in function in MATLAB called once, another one is called zeros. So once will construct a vector or a matrix of a certain size. So it takes two arguments, 1, n. Okay. So in this case, it's going to create a vector with 1 row and n columns. So it will be a row vector of ones. Okay, and that, I multiply that by d, which comes from here. So that creates a vector of d, the diagonal elements. And I pass that to a function called diag, which puts it on the diagonal and returns a matrix. So the first part of this code is going to return a diagonal matrix with d on the diagonal. Okay. The second part of the code does exactly the same, but if you go off diagonal one element, you're going to get n-1 entries in there. So I need to assemble ones with a length of n-1. Okay, and I multiplied by L, the lower one. And you have to be careful with L and -1. They look very close. Okay, but this is L and this is 1. Okay, the -1 indicates, puts it on the lower diagonal element, and that will return a matrix with zeros everywhere, but below the diagonal, non-zero entries with L in that. And the same thing is done on the upper diagonal one. And so if I pass this, it's going to return a certain matrix T. Okay. So the first thing I need to do is T is equal to T bar ID 1, 2, 5. So I've generated a 5 by 5 tridiagonal matrix using that in P. Now to answer your question, how do I construct B? Suppose the first element is number 2, and then I need n-2 entries. The length of vector B is n. Okay? So I need n-2 entries. So I put zeros, 1. When I put a semicolon here, that implies that I'm going to go to the next column, right? And then I need to put a column matrix. So I need n-2, 1. So that will produce an there are a lot of surprising cases. Maybe I'm wrong.
No, that'll work as long as you tell it what n is, right?
Yeah.
Pardon me? Oh, yeah. I need to tell what n is. Thank you. So, 5. In this case, n is 5. You get the idea, right? So, in this case, I'm constructing a 5 by 5 matrix, so I need 3 zeros. And the last element, which could be 1 or whatever. Okay?
3, 2 will generate a matrix.
3, 1. There. Does that answer your question? That's what you need to do. Okay. Now, there is a function that I wrote called power I, power iteration. And that's how it looks. Okay, so it actually returns the Rayleigh quotient that we talked about in the last class, which is an estimate of the eigenvalue and the corresponding eigenvector that goes with that largest eigenvalue. So to the power matrix, I pass the matrix that I want to work on, T in this case, and the maximum number of iterations, how many tries I want it to make, for example. So here I've set maximum iterations to 100 if you don't provide a number. Okay? So these are the fancy checks and bells and whistles that most of the well-written MATLAB programs will have coming from MathWorks. Okay? So they will allow you to put, for example, only 1 input argument or 2 input arguments or 3 input arguments. How do they know how many arguments that you have given? So there is a function called, a variable called NARGIN. It's a built-in variable. So it knows how many arguments you have passed when you're calling it. And if it is less than 2, that means the user has not bothered to give maximum number of iterations. Then you set a default value inside. These tricks you need to learn. If you have to use these things, get it to do what you want it to do. So you try it and it says that it is not converging or it is not found. So then you need to be able to figure out, okay, how do I manipulate the maximum number of iterations or the tolerance? What do I mean by these things? So those are, from a practical point of view, you should have an idea of why we need it and then how we manipulate it in a given software. Okay. So then I find the length of T to find the matrix and I generate a random vector. That's my initial guess. The idea is that the random vector will contain components in all directions. That's very key. Okay. If you provide an initial guess that does not contain a component in the direction of the largest eigenvector, what happens? It goes to the second largest eigenvector, right? So we saw the reasons for that in the last class through the spectral representation. So if you pick a random vector, the hope is that it will have components in all directions, including the first. We need certainly in the direction of the first, the largest eigenvector. And then this is the normalization scheme, and then I'm setting up a while loop. While the difference between the new vector and the old vector, the norm of the new vector and the old vector, remains large, and the count remains less than the maximum number of iterations, keep doing the power iteration scheme. Okay? And if it doesn't converge in that scheme, then you check whether the count has exceeded the maximum number of iterations, put an error message. Otherwise, pack the vector v with your eigenvector estimate, and pack the variable Rayleigh q with the eigenvalue estimate. And those are the two that are returned. Okay? So to use this, it's fairly easy. Okay. So I did not bother to give how many iterations. So hopefully it converged. But in this particular case, I can actually check max. So I want, the reason I am kind of pointing these out is I want you to be able to not just listen to the lecture to get the bigger picture, but the actual learning occurs when you do these things on your own. So the purpose of the assignment is to explore some of the things that I think are important, but we cannot obviously cover all the aspects that we do in the lecture. So play with it with MATLAB so you get better at MATLAB and also at implementing some of these concepts. So you get rid of that fear, okay, of it's a complex concept, I cannot understand it. It's really not very complex. Okay, so I have given you for the other ones, the inverse power iteration, so you can generate a matrix, and I will put these two codes and we can play with that. Okay, so any questions? No? Did I start the recording? Sometimes I get these. Okay, any questions from the guys at the PI? No questions? You guys are doing well? Okay. All right, so the next idea is the spectral representation of the solution. You will never do this because it's a very inefficient way of doing it. But you should have a conceptual understanding of what it does, because the power behind this is the idea that we are going to develop here is implemented in most packages like COMSOL for differential equations. Okay, so what is the idea? If you give me an equation AX equal to B, the most efficient way of solving that is LU decomposition. Okay, and if it is sparse, there are sparse versions of the LU decomposition that are available. But we saw matrix inverse, we saw Cramer's rule. Those are all very easy conceptually to understand, computationally very inefficient. This one gives you a different perspective on the solution procedure. What is it? So if you give me A, I can find the corresponding set of eigenvalues and eigenvectors. Lambda I, we call it as EI. So I'm going to have n such values. We'll take, for example, A to be symmetric, positive, definite. So these are all well behaved. There are no degenerate cases. Okay, you're just trying to get the idea. And degenerate cases, you need to work harder to take care of the exceptional situation, but the concept remains the same. Okay. So what this is called a spectral representation. So what we are saying is the solution to this X can be represented by its spectrum. Okay. So what we need to do is we take the known vector B and construct its spectral representation through this. Okay. All we are saying is if you give me a vector, arbitrary vector, and if Ej is the basis vector, I can construct that arbitrary vector as a linear combination of those basis vectors. Right? Any questions? Do you understand that idea? This is an important idea. We keep repeating it later on. So instead of basis vectors, we'll be talking about basis functions. Finite element method, for example, is built on that idea. Okay. So here the eigenvectors form a basis. Why? Because they are linearly independent. Right? So I can represent any arbitrary vector in terms of this. So I know B, I know the eigenvectors, the basis vectors. But what I don't know in this one is beta. I need to find that. If I can find that, I have a spectral representation of that particular vector. That is, I have broken down that arbitrary vector in terms of its components. Okay, and once I do that, I can then write X also in the same way in terms of its spectral representation. So the spectral representation for B simply means find the coefficient beta. There are n coefficients beta. Find those coefficients beta, you have a spectral representation because everything else is known. In the same way, if I write X in terms of its spectral representation, so X is an unknown vector at this stage. Okay, this is what we want to find. Okay, so that remains an unknown. But so does alpha. But I know Ej, the basis vector. So in order to find X, all I need to do is find alpha. Then I can plug the alpha in and I have the solution. Okay. So, but the process requires you to know what A is and construct its eigenvalues and eigenvectors. For large system, that's not possible. Okay. So it's just a conceptual understanding that we want to develop from this. So with these two spectral representations, I take the original equation AX equal to B and substitute for X on the left-hand side. So it is alpha j Ej, A times alpha j Ej. On the right-hand side, B is represented by Bj Ej. Summation over all the eigenvectors, the basis set. Okay, but A times E is the same as lambda times E. That's a definition, right? So I can replace that, and then I can combine the two terms. Okay, Okay, so take this to the left-hand side and write it as lambda, so term by term, lambda here, alpha there, and beta there. And they all can be factored out and written as multiplied by Ej. Summation over all j is equal to 0. Okay, but now what do we know about Ej? It's a basis set. That means it's a linearly independent vectors, right? So the only way I can satisfy this equation is if this is the notion of linear independence. If a set of vectors are linearly independent, the only way that you can satisfy this equation is having the coefficients for each one of the entries as equal to 0. So for each j. And that allows you to calculate what alpha j is if you know beta j and lambda j. Lambda j we already know the eigenvalues. So we have reduced the problem to one of finding the spectral representation of the forcing function on the right hand side. If you know the spectral representation of the forcing function, then you can find alpha and you can plug it back and you can construct a solution. Okay. So do you know how to get beta? How would you get beta? I guess I haven't put that part in here, but I just realized that the problem is not complete until you know how to get beta. So you should have actually asked me, how do I get beta?
It will be linear system of equations.
Yeah, there are a couple of ways of doing it. One is just expand this. Put the vector b in here, put all the eigenvectors, and beta will appear as coefficient. So it will be a linear system of equation. Instead of solving the original linear system, you need to solve a new linear system of the same size. So it is certainly a valid way of doing it, but you won't do that. What if you are smart? What else can you do?
Do you know the basis for Graham-Schmidt?
Is it loud?
Graham-Schmidt orthogonalization of B. They are all linearly independent. You already know the basis.
They are all,
then calculate your beta Graham.
right. So you use the property of orthogonal vectors. Okay. So if the basis vectors turn out to be orthogonal, if they are not orthogonal, you can always construct an orthogonal set using Graham-Schmidt procedure. But if it is symmetric and positive definite, you will get them to be orthogonal.
Eigenvalues aren't necessarily orthogonal.
Pardon me?
Eigenvalues aren't necessarily orthogonal.
The eigenvectors?
Yeah,
The eigenvector depends on the matrix property. If it is symmetric and symmetric, you will get an orthogonal set. One of the assignment questions is exactly that. Show that the eigenvectors are orthogonal. If you haven't come that far, you will come to that. Okay. But we also saw in the class, if it's not symmetric, what happens? You have a left and a right eigenvector, but they are bi-orthogonal. Okay, so you can use those properties. Okay, but in this case, I've started by saying it is symmetric, so it is orthogonal, so I can use the orthogonality property. The reason I'm talking about this is we'll repeat the same thing. Okay, when you go to functions, we'll have functions that are orthogonal, and we will use that orthogonality property. So how can I do that? All I need to do is take this equation, take that equation and multiply it by EI. Take the inner product. Okay, so B dot EI, that's the inner product, which will be a number, okay, between the vector B and E. And that should equal, on the right hand side, I will have beta j multiplied by EI EJ. EI dot EJ. Okay, summation over all j. But since these are orthogonal, only when I is equal to j, it will be 1. All the other terms will be wiped out. Okay, so that will reduce to simply beta I. That's it. If they're orthonormal, the inner product between EI with EI will be 1. Okay, so that's how you get the beta I coefficients without solving the system of linear equation, using the fact that they are orthogonal. Okay. So, as I said, it looks like it's a fairly simple procedure. All you need to do is construct the spectral representation of B, and you already know the lambda i's, so you can calculate alpha i's and you can plug it back in. But the key computationally demanding task is finding all the lambda i's and finding all the ei's for large system. Okay, so you will not use that one. Any questions? So the next idea is minimizing the residual. This is also an idea. It's easy to grasp and understand with linear systems, but we will apply that in method of weighted residuals and all the methods that we are going to develop later on with differential equations. Okay, so here you are given once again an equation Ax equal to B. Okay, but this case it's not an n by n system. Okay, A is an m by n system. And so x is an n by 1 vector, and b is an m by 1 vector. And m is greater than n. What does it mean? It means we have more equations than unknowns. Okay? There are more equations, more constraints than there are unknowns. So can you solve the problem? You can solve it in the least square sense. That is, find that vector x that minimizes the residual. That's a key idea that I want to focus on. So you cannot find a vector that will exactly satisfy all of those m equations because you have more equations than unknowns. Okay? So if you take, for example, the first n equations, you can find a solution, but it's not going to satisfy the remaining equations in there. So MATLAB will handle such cases, okay? And it will use the idea that we are going to see, and that is find a residual vector as ax minus b. That is, take the difference between the left-hand side and right-hand side, and that will give you a vector r. What will be the size of r? M, right? Because there are m equations to begin with, so that will be m. And define an objective function based on the residual, and the objective function is going to be simply the norm of that residual. Okay, and that is ax minus b transpose multiplied by ax minus b. So that is a scalar function. Okay, a norm is a scalar number, so it's essentially we have two vectors, but I'm converting that as an inner product between those two vectors. So this phi is treated as a function of x. So as I search for different values of x, phi will change, and I can plot them. Okay, so if I plot this, x and phi, that's a quadratic function in x. Okay, so the function will have a shape like this. It need not touch 0 at the bottom. Okay, so the residual will not be 0, but what we want is find that value of x where the residual is the minimum, the lowest. Okay, so we convert the problem to a minimum residual minimization problem. And what this means is, if I take x, some value, if I perturb that x arbitrarily, positive or negative, and I want that x plus delta to be, phi at x plus delta to be greater than phi at x. Simply means if this is my optimum value, and if I perturb it by a certain amount, delta, I must always get a number that is greater. So if I take 2 points here arbitrarily, that won't happen. I might get lower or higher. But if I am at the minimum, then as I make this delta arbitrary, this is key. Delta is an arbitrary vector. X is the vector that I'm interested in, but I perturb that vector by another vector which is arbitrary, and I want to find that value of x which always gives me a greater value for phi, for arbitrary perturbation. This is function minimization idea you will see in calculus. How many of you have seen calculus of variations? Variations. Calculus of variations. Have you heard about it? It's the same idea as in calculus for minimization of a function, but now you are solving function of a function. Okay? And we will review that later on. I'm kind of reviewing this and pointing where you will come across this again when you're doing differential equations. Okay? And that is really the key in this course. We want to learn how to solve models that result in ordinary or partial differential equations, but the ideas are all already embedded in here. Just want to extend them. So minimization of a function by simply using ideas from calculus, or minimization of a function which is called a functional which is the calculus of variations. Now, this minimization will give rise to an equation called a normal equation. If you do that in calculus of variations, what do you get? Because only one or two have taken that. Do you remember? Euler-Lagrange equation. Okay, you get, by minimizing that, you get an Euler-Lagrange equation. So often solving the Euler-Lagrange equation is exactly the same as minimizing a functional. And in method of weighted residuals, we formulate that and we see whether we can construct the Euler-Lagrange equation that corresponds to this. So solving that differential equation means minimizing a corresponding residual. Any questions? Now the manipulation starts. We have laid out the big picture. We have an undetermined system, more equations than unknowns, and we want to find the best solution possible that does not necessarily reduce the residual to zero, but minimizes the residual. Graphically, that is the picture, but it is a simplistic picture. Remember, it is not a parabola in one dimension, but it is a higher dimensional system. Okay, so it is a quadratic equation. So we start with the expression for phi, which is ax minus b transpose multiplied by ax minus b. These are two vectors, row vector with a column vector. So inner product, that's a scalar number. So every term on this must result in a scalar number. But it's essentially an expansion. So if you look at term by term, it's going to be difficult for me to show, but let me see. So I'm going to multiply this ax transpose with ax, and that gives me this. Okay, so you know this result. Ax transpose is x transpose A transpose. Okay, so using that, applying the transpose operator, you'll get x transpose A transpose multiplied by Ax, which is the second part. Okay, then you take the next term, which is this one with b. Okay, so that gives you x transpose A transpose. And then you take B transpose, okay, with AX, which is this one. And that gives you that. Okay, and finally B with B transpose with B itself. Okay. So this with this. So just a straightforward expansion. Okay. But remember, each one is a scalar number. Okay. So we take the first term as it is, x transpose A transpose AX, minus, we combine these two terms, okay, x transpose A transpose B and B AX, because if you transpose this, you will get the other one, and they are exactly the same number. Okay, so I can combine that as twice x transpose. So this one is the combination of these two terms plus B transpose B. So once you have expanded that, you try to find this criterion. The criterion is phi at x plus delta minus phi at x must be greater than 0. Okay, so I try to construct that difference using this value. So I substitute this value here, and I replace what phi x is before. So if you look at this term, this would be x plus delta, right? So it's x plus delta. So what did I do here? I took exactly the same template that I had from previous one, but wherever I had x, I replaced it by x plus delta, x plus delta, x plus delta. Okay, and the second part is this, which remains as this one. Okay, now once again you need to expand these terms and then cancel them. So I hope you can spend some time after the class to carry out this step. Okay, so which requires you to expand this thing in detail and then cancel with the terms, the corresponding terms on the right hand side, and simplify this term into this particular following form, the last term, which is A delta the norm, which would be something like delta A transpose A delta. These are the same terms. That is the norm of that particular quantity. And then twice delta transpose. Okay, so these will be terms like this that you're combining, and the other terms will cancel out. multiplied by A transpose AX minus A transpose B. We want this to be greater than 0. We want the left hand side minus right hand side of this to be greater than 0. So we want that to be greater than 0. Okay? The idea is exactly the same as you would find out in taking the derivative of a function. Okay? So the interpretation now is delta is an arbitrary vector. It cannot be a 0 vector. Okay? It has to be arbitrary vector, so this cannot be 0. Okay, so what we want to do is we want to satisfy this condition that this term on the left hand side must always be greater than 0. Okay, so the first term cannot be 0. It has to be a positive quantity. It's a quadratic term, square term. Okay, but the second term can be positive or negative because I can make my delta to be negative. Delta is an arbitrary vector that I choose, right? It's a perturbation that I choose. So I can make delta to be large negative values to violate this condition. Even though this is positive, if I pick delta to be a large negative value, the whole thing will be negative. But I want it to be positive, right? So how do I make sure that it will always be positive? What condition must be satisfied so that this left hand side will always be greater than 0? Okay. So since delta is arbitrary, I need to have this as equal to 0. If I make that equal to 0, then I don't care about delta. You make delta to be anything that you want, that condition will always be satisfied. Okay, and that is called the normal equation. So satisfying this normal equation will ensure that you are minimizing that residual. So minimizing the objective function that I have defined, which is the norm of that residual vector. Okay, minimizing that is equivalent to solving this normal system. So I don't really have to, I can use the same machinery that I have developed. The only thing I need to do is, I need to construct a new matrix A transpose A. I need to construct a new vector A transpose B. You're going to give me A and B, right? But A will be m by n and B will be m by 1. But I can take A transpose and A. What will be the size of A transpose A? If A is m by n, A transpose A will be m by n, n by m. No, sorry, n by m, n by n, n by n. So you have once again a square matrix that is well formulated.
It's also guaranteed to be SPB.
Guaranteed to be?
Isn't it true? When you take A transpose A, isn't that guaranteed to be symmetric? Positive?
Yes, it will be guaranteed symmetric positive. Yeah, SPB, symmetric positive, definite, right? Yeah.
Real quick, at the beginning of the whole process, during the first factorization, you have X transpose A transpose B minus B transpose AX, and you said that they're equivalent.
Yeah.
Is there a quickie way to prove that to me, or do I need to go through it to check myself?
X transpose A transpose B and B transpose A X,
Yeah.
are they the same?
I mean, you said they were the same.
They are the same. Is there a quick way to show that?
Yeah, to prove it. to make
Yeah,
sure.
yeah. If I have a scalar number, if I transpose that, it's the same scalar number, right? So every one of the terms in here is a scalar number, right? So if I take this term and take its transpose, it's going to be the same number, right? So if I take the transpose of B transpose AX, transpose of that, I will get the same number as I have the other at the other place. Now expand that. You have to apply 2 at a time. So you can do AX transpose B, and then you apply to this one more time, and you'll get that. Right.
All right.
So
Yeah.
why the residue always be positive? Can it be 0?
Yeah, the question is, why should the residual be positive? Can it be 0? And the answer is, it can be, but it will be very coincidental if it really does happen. Okay, because you have more equations than unknowns. Okay, so you might have a situation where the first n by n equations gives you a solution that also satisfies the remaining equations, but it's going to be pretty rare. Okay, so the best that we can guarantee is that it will be the minimum. Will that minimum also be 0? Often it will be a degenerate case if that happens, a special case. Okay.
Also for the last
Yeah.
so for the term in the parentheses, can it be negative to keep it positive?
Can this be negative?
Uh-huh.
That's also possible. Those are all exceptional cases. We want to look at the most general case. How can I guarantee if delta is any arbitrary number, how can I guarantee that it will always be positive? I can always guarantee that it will be positive if I make this equal to 0. Okay? But there may be other situations where you can also satisfy this. Those would be exceptions to the case. Yeah. So solving this equation, did I not write it down? Yeah, here it is. So ultimately the problem is given Ax equal to b, where A is not a square matrix, forming this so-called normal equation and solving that is equivalent to minimizing the residual, that the objective function that we form based on the residual, minimizing the error, minimizing the sum of square errors, least square. So it's a basis of the least square method if you like. Okay, any questions? Any questions at the PI? No? Okay. At least two guys are paying attention. Oh, okay, more than that. All right. So, conjugate gradient method. It's an iterative method, an important method. I'm not sure whether I put this in the right order in terms of covering the material, but I thought I should talk about it before we go into dynamical systems theory concept. So what is a conjugate gradient method? It's an iterative method, just like successive over-relaxation, Gauss-Seidel, Jacobi iteration. It's an iterative method for solving large linear systems. It's a commonly used method. It's available. The code is available for download from most places, including MATLAB has built-in conjugate gradient method function. And there are a whole class of methods that are built on that, extending this idea. So I thought we should at least understand the basic idea, and the embellishments on that would be like from power iteration to Arnoldi scheme, for example, expanding from one-dimensional subspace to an n-dimensional subspace. So the conjugate gradient method is, this material is taken from the Wikipedia, so I've given you the reference here. So if you want to learn more about it, and there are references to the biconjugate gradient, the preconditioned conjugate gradient, there are a lot of other variations on that. All of them are documented very well in that website. Okay? So the basic idea that is illustrated here is, if I have a quadratic function and I plot the quadratic function so it's a function of x1, x2. And so I'm plotting x1 against x2 with that function. So how will that function look? It will be a, this is equal to some constant. Okay. So this will be a surface like this. Okay. So I'm going to take a simple case where the surface is a parabolic antenna dish type of a structure. Okay. So you can cut that surface at different values of the function, and those will be called the contours of the function. So a contour is like this. So on that contour, the function value is a constant. Okay. So its function value is a given constant, and that gives you a contour. Okay. So what we want to do is, we want to, again, it's the idea of minimization. Okay, minimization of the function. So we want to find that particular location. Okay. So we start with some initial guess. Okay, and we find the direction vector. So this is my initial. Now you have to imagine, I'm illustrating from a two-dimensional case, but imagine it's an n-dimensional case. So you have an n-dimensional vector, and from that vector you have to find out the initial direction in which you want to go towards that solution. The solution is, for example, at the minimization of that particular point. So if these are the contours, where is the direction in which the contour is changing at the fastest rate? If I go along the curve, the derivative of the function would be 0 because the function is constant. So it must be perpendicular to that, right? So that is the direction of, sometimes called steepest descent, okay? The direction in which the vector changes the most. So you need to find that vector. Instead of making an arbitrary guess for a vector and then multiplying it by the A, getting a new vector which gives you to the largest eigenvector, we want to find a method which goes to satisfying that equation Ax equal to B, okay, in an iterative method. That problem requires you to make a guess for a vector, find a new vector, and apply the method repeatedly. So that requires us to find the direction in which I should go, and I'm going to say that the direction is the direction in which the function changes the most rapidly. Okay, so that gives me a direction vector. The next thing I need to find out is, okay, I know the direction I need to go. How far should I go in that? So I need to find the factor or the distance over which I should go in that direction. Suppose I make these two choices in an optimal way, the direction and the distance over which I need to go, and I end up with a point here. Starting here, I end up here after determining these two, direction of the vector and the distance I need to travel. Now I need to repeat the process. So at this stage I need to find out, okay, what is the direction in which the function is changing the most rapidly? And it turns out it is in this direction. And I need to find the distance over which I go. And I repeat that, and that leads to convergence in a very quick succession of iterative methods. That's the basic geometrical idea of conjugate gradient, and the whole class of methods that are based on that, the steepest descent method. It came from optimization, okay, of a function. Any questions on that, conceptually? Okay. Computationally, how do we implement that into a particular algorithm? So here, this entire material is taken from Wikipedia. Okay, I just cut and paste from there, and it's really nicely done. We are going to first have to generalize this notion of perpendicularity or orthogonality. We just said that two vectors are orthogonal if the inner product is 0. Okay, but here we are introducing something called a conjugate vector. Okay, so we say the vectors u and v are conjugate, a more generalized version of this perpendicularity. And again, we will see this later on with the method of weighted residuals. We will say the two functions are orthogonal to each other with respect to some weighting function. So in the same way, these two vectors are orthogonal to each other, not directly. That is, if A is I, then they are orthogonal to each other in the traditional sense. That is, the cosine of the angle between those two vectors is 0. Okay, but sometimes you need to use a weighting factor A. Okay, so you form a new vector which is A times V, and then take the inner product with U. And if that happens to be 0, then they are still, we can call them as orthogonal with respect to this weighting matrix, weighting factor, or they are conjugate. That's the terminology that they use. Okay. So if A is symmetric and positive definite, then you will find that UV is orthogonal. It's written, the inner product is written in this form. UV, that is, means the inner product between these two in this notation. Notation would vary from book to book. Sometimes you will see U dot V, sometimes you see this bracket, and here we are introducing this A to indicate that it is orthogonal or conjugate with respect to that weighting function. The meaning of that, that is the definition of this is AU comma V. That is the inner product between the vector AU and V. The product between A and U will give you a new vector. Okay, the inner product between that vector and V, or the inner product between U and A transpose V. They are all the same if A is symmetric. Okay, or the inner product between U and AV, or the same as this term that we talked about. Okay, if A is symmetric and positive definite, this is a notion of orthogonality generalized with respect to a weighting function in that space. we already talked about the spectral representation of the solution. The reason that I introduced that is it comes in handy in developing the conjugate gradient method. Okay, so we have this equation Ax equal to b, and we are saying that pk, a sequence of vectors pk in that space of n dimensions. So there are n vectors pk, and they form the basis. Okay, they are mutually. There are a sequence of vectors that are mutually orthogonal, conjugate, orthogonal with respect to that weighting function. Okay, so we can expand that solution x star in terms of its spectral representation. This means that we are not going to do an eigenvalue analysis. In the spectral representation, we actually did an eigenvalue analysis. We found out what these vectors p are, and then we said, okay, I'm going to find the alpha using the orthogonality property. Okay, that's a computationally expensive way. So we are not going to do that, but we are going to estimate using the ideas from there. It's not strictly a spectral representation, but we can always, you don't have to have the eigenvectors as your basis. You can always construct n mutually orthogonal vectors as the basis in a space, and you can represent any vector in terms of those basis vectors. So we are going to construct these vectors to be orthogonal to each other as we go on the fly. What that means is initially I'm going to be blind. When you give me Ax equal to b, I don't know where the solution is. I'm going to make an arbitrary guess for a vector. That gives me a direction, and in that direction I'm going to take a certain distance. But the next vector I need to guess, I'm not going to be arbitrary anymore. I'm going to say I want that to be perpendicular to the original one. Okay. So as I go on in this iterative sequence, I'm scanning the space in such that every time I go perpendicular to the previous one, so I go into new parts of the space, and so I'm reducing the residuals of new components of the vector. Okay, that's a basic conceptual idea behind this. So I take this solution vector and represent it as a linear combination of this sequence of vectors which form the basis vectors. Okay, they are conjugate directions. So it's exactly as we did before. Okay, so b is equal to ax star is the equation. B equals ax is the equation, but x is being represented in terms of this vector, these basis vectors. Okay, so I'm going to make that substitution, alpha times bi. So because I have a here, and I will have a there. So this is the equation that I'm starting with. The equation is given to me: b equals ax, or ax equal to b. So I'm writing b as ax star, and ax star is represented in terms of that basis vectors b. I don't know the p's right now. We're going to develop them. We're going to develop a sequence. That is the essence of the conjugate gradient method. Ideas are very similar, but implemented in a different way. Okay, so what am I doing here? Let me ask you, see whether you can. When you read these kind of algorithms, you should develop the ability to conceptually say, okay, this is what is happening on this stage. What is happening on the line that I have indicated? You guys at PI also think about it as you're going along. What am I trying to do? Why am I taking the pre-multiplication of b with respect to pk? Okay, I'm pre-multiplying everything by pk transpose. Okay, why would I do that? In the spectral representation, I did the same thing, and I used the property of orthogonality to find the coefficients beta. Okay, so here I'm doing the same thing. So by pre-multiplying this by this, and then ax is given by here. So I have the pre-multiplication vector. This is the same as this, which is the same as this. So the equation remains the same, except I'm pre-multiplying everything by b transpose. And here I have a summation term. And the question is, how did the summation term become that? The summation is over all I, but I'm pre-multiplying it by k, pk, right? It is using the extended notion of an orthogonality property of this basis vectors pk. Okay, so only when k is equal to I, that will be non-zero. For all other terms, it's going to be 0. So that gives me the equation as alpha k equals pk transpose A pk. Okay. From that, I can find out what alpha k is. Okay, if I know pk, right? In the spectral representation, I know pk because they are all the eigenvectors. But in the conjugate gradient method, pk is something that's going to be dynamically determined to be just perpendicular to each other. So you cannot interpret that as eigenvectors. Okay, but we know b and we know a. How about all the pk's there? That's what we need to determine. So initially we are going to say an arbitrary direction, then we are going to construct them dynamically as we are going to apply the iterative scheme. Okay, I think we are term. So so here is the basic idea behind the conjugate gradient method. So we talked about earlier how to construct this vector and how to determine how far we have to go in that vector using this generalized notion of orthogonality. The actual conjugate gradient method is given the equation ax equal to b, I construct a objective function, convert that into a minimization problem. Okay, so the minimization of that objective function is the same as solving that equation. We actually applied that to a not square matrices before, but here this could be a square matrix. Okay, so my new objective function that I'm going to define, f of x, is simply 1/2 x transpose A x minus x transpose b. This is my definition. What is given to me is simply this: ax equal to b, and find x. So I'm given a and b and find x. That's the problem that we are solving. But I take from that ax minus b and pre-multiply by x transpose, and I put a half, and I say that is my objective function. Why did I put a half? Just for convenience. But what you need to do is, you need to recognize right away why I would do that. I would do that because this is a quadratic function, and the function f of x is going to be something like this. And I want the derivative of that function to be equal to 0. Okay? When I satisfy that condition, I will be solving this equation. Okay? So what is the derivative of that function? By simply applying chain rule. So you need to apply chain rule. A is a constant, so x appears twice, x squared. So when you take df dx, it's going to get 1/2 times, let me take the derivative of x transpose with respect to x. What will that be? Do you know how to take a derivative of one vector with respect to another vector? Just an identity matrix. Because you're going to take, when you do derivative of x, a vector x with respect to another, the same vector x, all we are doing is we are taking derivative of component 1 with respect to component 1, component 1 with respect to component 2. Those will all be 0. Okay? So this will give you an identity matrix. So you will get I times ax. So in the first part of the chain rule, I have kept ax together and I have taken the derivative with respect to x transpose. Then I need to take the derivative with respect to x, right? So I will have plus x transpose A. What would be derivative of x with respect to x? Again, I. Okay. And the derivative of, sorry, I should have the other one too. X transpose B. What will that be? Minus B. I want that derivative to be equal to 0. Okay, I want to minimize that objective function, right? And of course, IA is the same as A, and AI is the same as this. And so I get x, AX plus x transpose A. Right? And that is the same as, if A is symmetric and positive definite, it's the same as AX. So that's why I have the 1/2, so to cancel that. And what I will get from this one is, that implies that AX minus B is equal to 0. So in the conjugate gradient method, what we are doing is we are actually minimizing this function, but that is going to find us the solution to that particular problem. Okay, that's the basic idea. I think we have run out of time, So maybe we will start from this place on Wednesday. Okay, constructing the residual vector, going through the logic for. Basically, we need to develop a logic for finding the direction, finding the distance we have to go in that direction, and repeat that process. And that is the conjugate relating method. Okay, so we will see that in the next class. Okay. Okay, any question, guys, online? This is a large number participating in online now. That's good. I hope you guys are finding it as, in terms of learning, as the same as being in class. I can ask these guys questions and respond to them, and that we are not able to address yet effectively, I think. So we need the audio also for that part from you guys. So send me your feedback on how you find that lack of interaction. Is it hurting your ability to ask questions? Of course, you can always email me and I'll try to answer that. Okay? All right, see you on Wednesday.